Okay, let us start the lecture. Today we will discuss Lebesgue measure on Rn. Lebesgue measure on Lebesgue measure on Rn. So let's define this class of sets. Let S is equal to the product of these semi-closed intervals. I runs from 1 to n such that ai, bi, they are all real numbers where this product is I runs from 1 to n, product I runs from 1 to n, ai, bi is equal to the set of n tuples. Actually it's a product of n semi-closed intervals, so it's like this: x1, x2, xn, such that this ai, it's less or equal to xi, less than bi, 1 less or equal to I, less or equal to n. If ai is less than bi for 1 less or equal to I, less or equal to n, तो ये प्रोडक्ट इसके बराबर है. And this product is the empty set, and this product I runs from 1 to n, ai, bi is the empty set if for some I, पर किसी एक I के लिए आपके पास रिवर्स इनइक्वालिटी हो, ai greater or equal to bi, किसी एक I के लिए. So that means this, the class of these product of n copies of semi-closed intervals, it contains the empty set. ये empty set को contain कर रहा है, और ये इसको भी contain set of n tuples. Okay, it's so this is a class of n tuples actually. Okay. So then we know that this SS semi-ring that we have already proved. Then जब हमने Lebesgue measure R पर डिफाइन किया ना, वहाँ पर हमने एग्जांपल ली थी. अगर हम इसको n equal to 1 के लिए करेंगे ना, इट्स जस्ट द क्लास ऑफ सेमी क्लोज्ड इंटरवल्स ए बी है ना, तो वो हमने चेक किया था, वो सेमी रिंग है. और फिर हमने जनरल भी प्रूव किया, एस एन को हमने इंडक्शन से किया था, बाय यूजिंग इंडक्शन ऑन एन. तो वो हमने किया है प्रूव. दिस इज अ सेमी रिंग. देन एस इज अ सेमी रिंग. एस इज अ, it's a semi ring. Okay, it's a semi ring on the set Rn. Okay, on n space. Now we define set function on this S, and we'll show that that set function is a measure. Okay, that's the next theorem. The set function lambda, the set function lambda from semi ring S to 0 to infinity defined by lambda of the empty set is equal to 0 and lambda of non-empty set, that's the product I runs from 1 to n, ai, bi it's equal to the product of lengths. Product I runs from 1 to n, bi minus ai. Where each ai is less than bi, where ai less than bi for I runs from 1 to n. Make lambda of empty set is 0 and the lambda of this product, which is a non-empty set, it's equal to the product of lengths. So where ai is less than bi for I runs from 1 to n. The set function lambda defined by this is a measure. Is a measure. This is a measure called the Lebesgue measure. Okay, this is a measure on S. It's a measure on S. It's called the Lebesgue measure. Called the Lebesgue measure. इस measure को हम Lebesgue measure कहते हैं. Okay, so we use induction. Let's denote this set function lambda by lambda n. Proof. Let's define. Let's take lambda equal to lambda n. Then we apply the induction on n. Let's do this. Let Sn जैसे हमने वहाँ पर किया था, Sn is equal to product I runs from 1 to n ai bi, where ai and bi they are real numbers, and lambda n is a function from Sn to 0 to infinity, which is defined by lambda n of the empty set is 0 and lambda n of this non-empty set, which is the product of n copies of non-empty intervals ai bi, it's equal to the product of the lengths I runs from 1 to n bi minus ai, where these ais they are less than bi's for I runs from 1 to n. So we show that this Rn x Rn is here, x is Rn, here x is Rn. Okay, so what's the notation for measure space? Is it Rn x mu, I think it is x then semi-ring. So this we show that this Rn Sn lambda n, okay, is a measure space. ये हमें एक्चुअली प्रूव करना है, measure space. So we need to show that lambda n is a measure on Rn actually. That's what do we mean by measure space actually. Sn is a semi-ring, lambda n is a measure on Sn. वही actually हमें prove करना है. So to prove we use induction on n. We use induction on n. Okay, for n equal to 1, what's s1? Then this s1, it's just the class of semi-closed intervals AB, such that AB belongs to R. And what's lambda 1? Lambda 1 of the empty set is 0, and lambda 1 of the non-empty semi-closed interval, it's equal to B minus A, where this A is less than B. Then we know that this lambda 1 is a major on S. ये हमने already किया है. Then lambda 1 is a major on a semi-ring S1, जो semi-ring है जो आपने already की है, on a semi-ring S1. So therefore this R1 S1 lambda 1 is a major space, is a major space. ये major space है. So thus result holds for n equal to 1. Thus the result holds for n equal to 1. Hold for n equal to 1. Yes, आप जोर से बोलिए. हाँ, ये हमने ऑलरेडी किया था, n equal to 1. इसलिए मैंने इसमें कुछ नहीं किया. मैंने डायरेक्टली कहा लैम्डा 1 मेजर है सेमी रिंग पर है, इसको मैंने चेक नहीं किया. और S1 सेमी रिंग है, तो मैंने कुछ नहीं एक्चुअली इसमें किया. तो ये तो मैंने वही रिजल्ट्स यूज किए जो ऑलरेडी आपने किए हैं. So assume result holds for n, we will show that it also holds for n equal to k. Assume that the result holds for, assume that the result hold for n, that is, this is the semi ring, this is semi ring, that's this one, Rn. Okay, then Sn lambda n is a major space. Okay, this is a major space. Assume this is major space. We show that हमें प्रूव क्या करना है, n plus 1 के लिए भी रिजल्ट होल्ड. We show that Rn plus 1, then Sn plus 1 and lambda n plus 1 is also a major space, is also a major space. ये major space है. तो मेजर स्पेस के लिए Sn plus 1 सेमी रिंग होना चाहिए और लैम्डा n plus 1 मेजर होना चाहिए Sn plus 1 पर. Sn plus 1 सेमी रिंग है क्योंकि हमने ऑलरेडी प्रूव किया. We know that this Sn plus, या आप देखिए चैप्टर 1 में हमने किया था, यूनिट 1 में, is a semi ring, is a semi ring on Rn plus 1. So we need to show that we only need to show that lambda n plus 1 is a major, is a major on Sn plus 1. यह हमें प्रूव करना है. Lambda n plus 1 is a major on Sn plus. First property is trivial because lambda n of the empty set is 0 for each n. So lambda n plus 1 of the empty set is 0. This is by definition of lambda n plus 1. Okay. अब हमें सिर्फ सिग्मा एडिटिव प्रॉपर्टी चेक करें. ओके, we only need to check the property, sigma additive property. Okay, for this we take a disjoint sequence. Let's take a disjoint sequence in Sn plus 1. So let this be the disjoint sequence. Okay, it is a product it's a product I runs from 1 to n. Okay, how do I write it? Okay, let me write it like this. Let an be a disjoint sequence in Sn plus 1 such that the union is again in Sn plus 1. Union n runs from 1 to infinity is in Sn plus 1. What's Sn plus 1? It's a class of product of n plus 1 copies of semi-closed interval. So both an and this union is the product of n plus 1 copies of semi-closed intervals. So then this union, so we can write this an, okay, union an. This can be written as an. It is it's equal to a what's this an, okay. So let's write here b notation, okay. I will use notation b here. B. This is notation b here, okay. B. Then this bn is equal to this bn, okay. Then what's this bn? It is the product of n plus 1 copies. It's like an cross an bn. Where this an, it is in Sn. See, that means an is product of n copies of semi-closed intervals. Then this an cross this semi-closed interval an bn, it is the product of n plus 1 copies of semi-closed intervals. So it is in Sn plus 1. So then bn is of this type. It is the product of n plus 1 copies of semi-closed interval. So I can write it as an cross an bn, where an is in Sn. That means an is the product of n copies. क्योंकि मुझे एक्चुअली इंडक्शन का पार्ट यूज करना है, तो an पर मैं इंडक्शन अप्लाई कर सकता हूँ. an पर मैं अलग से इंडक्शन अप्लाई करूँगा और इसको मैं अलग डील करूँगा. दिस an bn, इट्स अ सिंगल इंटरवल, सिंगल सेमी क्लोज्ड इंटरवल, तो इसके लिए भी मैं अलग से रिजल्ट से अप्लाई करूँगा यहाँ पर. So this bn is this of this type, and the union किस टाइप का होगा? union भी इस टाइप का होगा ना, and union bn n runs from 1 to infinity, it's equal to union an, it's equal to union an cross an bn n runs from 1 to infinity. क्योंकि यूनियन भी Sn का ही मेंबर है, इट्स आल्सो equal to the product of n plus 1 copies of semi-closed intervals, and let's write this as a cross a b, where a is in Sn. तो ये क्लियर हो गया आपको? ओके. So then you can see this. Then now let's find this characteristic function of the indicator set A cross AB. Okay, this is semi-closed. This is equal to, what's A cross this? It's actually the disjoint union, and we know that chi of the disjoint union is equal to sums. तो पहले मैं इसको यहाँ पूरा लिख दूंगा. It's equal to chi of union n runs from 1 to infinity an cross an bn, and this is a disjoint sequence, so it's equal to summation n runs from 1 to infinity chi of an cross an bn. A and B, okay, right? Chi of the union, this is disjoint union, it's equal to the sum. जो पहला लेक्चर हमने जो इस पर दिया था स्टेप फंक्शंस पर, प्रॉपर्टीज ऑफ दिस कैरेक्टरिस्टिक फंक्शंस. Okay, so now for any fixed, now for x, now for this point which is in, which is n tuple, which is in Rn, and take a real number. तो ये मैं अलग अलग क्यों ले रहा हूँ, क्योंकि मुझे एक्चुअली इंडक्शन का पार्ट यूज करना, मुझे n पर रिजल्ट ट्रू है. Now this now for this we have characteristic function of a evaluated at x, since x is in Rn, a is a subset of, or n, a is in Sn contains a subset of Rn. Okay, so this is well defined. सबसे पहले आपको ये देखो क्या जो आप लिख रहे हो वो well defined है कि नहीं है. आपने लिखा chi a of x, तो अब आपको चेक करना है कि ये जो x है ये भी Rn का ही पॉइंट होना चाहिए, और a भी सबसेट किसका होना चाहिए, Rn का, और वो है x n tuple है, so it's a point of Rn, और a है Sn का मेंबर. ओके, और Sn में कौन से मेंबर्स है, Sn में Rn के सबसेट्स है, so that means a is a subset of Rn, so it's well defined. And then I will write this characteristic function of the interval AB evaluated at t. This is also well defined because t is a real number and this interval is the subset of R. And this one it's equal to या अगर आप डायरेक्टली लिखना जो या ऊपर जो आपने आइडेंटिटी लिखी है अभी काई की, वहाँ से भी आप लिख सकते हो, या आप डायरेक्टली कर सकते हो. इट्स काई ऑफ ए क्रॉस इंटरवल ए बी है ना, या आपने शायद ये मुझे लग रहा है कि ये आइडेंटिटी आपने की है स्टेप फंक्शन के लिए क्रॉस प्रोडक्ट पर, जो ना लास्ट प्रॉपर्टी थी 7th, काई ऑफ ए क्रॉस बी इज इक्वल टू काई ए काई बी. क्या है ना, काई ऑफ ए क्रॉस बी इज इक्वल टू काई ए काई बी. So this is your set A, this is your set B. It's chi of A cross B. Chi of A cross B is equal to chi A chi B. It's a product here. Now I can apply. It's actually the cross. This is equal to chi of A cross A cross AB evaluated at xt, क्योंकि अब आपका जो सबसेट है ना ये Rn प्लस 1 का सबसेट है, तो यहाँ पर अब पेयर आ जाएगी Rn प्लस 1 की. बट दिस इज इक्वल टू द सम जो आपने भी किया, chi of A cross B is the sum actually. This is a summation. I runs from 1 to infinity, or n runs from 1 to infinity. That's one and the same thing. Summation chi of what, ai cross ai bi, okay, evaluated at xt. Now again you can apply chi of a cross b is equal to chi a chi b. Again you apply that property. This is equal to summation I runs from 1 to infinity chi of ai evaluated at x, then chi of ai bi evaluated at t. Now we fix x and we vary t. We vary t. That's we apply the first. We apply this property that r1 lambda 1 and r1 then s1 lambda 1 is a major space है, वो हम प्रॉपर्टी पहले अप्लाई, हम x को फिक्स करेंगे, t को वेरी करेंगे, और t को जब हम वेरी करेंगे वो यूज द प्रॉपर्टी दैट r then s1 lambda 1 is a major space. Okay, वो हम प्रॉपर्टी अप्लाई करेंगे. Let's fix x means the point of rn. तो फिक्स, फिर हम इसके बाद इसको भी वेरी करेंगे, फिक्स x which is equal to x1 x2 xn which is in rn. Fix this point and let's define this phi k t. It's a function of t. Now this is equal to summation I runs from 1 to k. Okay, जो आपने ऊपर जो आपने इन्फिनाइट सम लिया ना उसी का फाइनाइट पार्ट up to k. Okay, उसी का फाइनाइट पार्ट. This is chi ai of x into chi ai bi of t. Okay, आपने x को फिक्स किया, so it's you can treat this as a function of t now by fixing x. तो इसलिए आपने इसको phi k t से डिनोट किया. Now what is this phi k t? What is this phi k t? It is a stuff. It's a stuff function. You can see it's a stuff function because each set it's a finite valued. It's a finite valued. It's a stuff function, and because you can write this as chi of ai cross ai bi. Then the measure of ai cross ai bi is finite because they are all bounded intervals, actually semi-closed intervals. So each has a finite measure. So this is actually a step function. Phi kt is a step function. Phi kt is a step function. Then this phi k is as you can sub step functions. Step function with respect to x as well as t. फिलहाल हम ये t का यूज with respect to t हमें प्रूव करना है. Is so you can sub step functions such that its limit it increase it's actually increasing sequence, क्योंकि जब आप k को increase करोगे ना you are actually increasing the terms of the sum, so it's obviously increasing. उसको प्रूव करने की जरूरत नहीं. आप देखिए phi 1 क्या होगा, phi 1 होगी एक ही टर्म होगी आपके पास. phi 2 क्या होगा, it's the sum of two terms, I runs from 1 to 2. phi 3 क्या होगा, sum of three terms, and each term is non-negative. Each term is non-negative, so that means phi k is actually increasing. It's increasing at it increases. ये कहाँ increase हो रहा है? Phi k t it increases to phi k t is in it increases to yes. इसका लिमिट क्या है? It's this summation I runs of 1 to infinity obviously. So but that's equal to that. Okay, पहले मैं यहाँ पर पूरा लिख दूंगा. It's equal to summation. The limit is with respect to k. यहाँ पर मैं k लिख दूंगा. I runs from 1 to infinity lambda ai of x then chi ai bi t. Okay, you are fixing x, so I'm not interested in x actually. This is equal to, but what is this? What is this infinite series? It's equal to chi ax, जो आपने ये भी ऊपर वेरीफाई किया है. अगर वहाँ पर कुछ नाम भी लिखोगे आप chi ax, जो ना आपने एक्चुअली chi x से स्टार्ट किया था, chi ax, then chi ai this chi abt से आपने स्टार्ट किया था. का ABT से आपने स्टार्ट किया था और इससे आपने स्टार्ट किया था, फाइनली आप यहाँ पहुंचे थे इस सीरीज तक ना। तो ये इसके बराबर, इसका लिमिट इसके बराबर, ये भी स्टेप फंक्शन है, which is a step function, which is a step function, which is a step function. हमने एक रिजल्ट किया है, if we have a sequence of step functions which increases to a step function 5, then integral of 5 increases to integral of 5, ये हमने किया है। तो इसका मतलब है कि इसका इंटीग्रल जो होगा that will increase to the integral of the limit function. So therefore integral of phi kt, it's with respect to t limit, okay, this will increase to integral of what, the limit function. What's limit function? It's Lebesgue measure of, okay, it's not a Lebesgue, it's not Lebesgue measure, sorry, it's lambda, okay, characteristic function of Ax and characteristic function of ABT. Okay, तो अब थोड़ा सा अब इसको एक्सपेंड करेगी. व्हाट्स दिस एक्चुअली? इंटीग्रल ऑफ फाई के टी. व्हाट्स इंटीग्रल ऑफ फाई के टी? व्हाट्स फाई के टी? इट इज समेशन. इससे थोड़ा ये आपको क्लियर होगा अच्छी तरह से. आई रन्स फ्रॉम 1 to k. दिस इज हियर इट्स characteristic function of what set? It's ai of x, then characteristic function of this interval ai bi of t. This will increase to, we are varying t only, so this means this chi of ax, it is independent of the integral, because you are integrating with respect to t only. It's chi ax, then integral of this. Okay, मैं पूरा स्टेप ही लिख देता हूँ, अदरवाइज मुझे यहाँ ये फिनिश करना था. दिस i of chi ab of t. Okay, this implies, now what is this? सम को हम बाहर निकाल सकते हैं इंटीग्रल, बिकॉज वी नो दैट द लीनियर प्रॉपर्टी ऑफ दिस integral of step function, integral of phi plus psi equal to integral of phi plus integral of psi. So we can this sum will be here, like I runs from 1 to k, then integral of this function again, this chi ai of x, it's independent of the integral. इसको हम बाहर निकाल सकते हैं, and here it's just integral of what function? Integral of chi ai bi of t. This will increase to chi ax. Now what's the integral of this step function? Chi abt. It's the Lebesgue measure of ab actually, है ना. इसका इंटीग्रल क्या होगा? Lebesgue measure of the set. It's in Lebesgue measure of ab, not lambda star, because we have here member of some ring. In fact it's here lambda 1. और हम ये क्यों कर सकते हैं? with respect to t हम क्यों कर सकते हैं ये? because we know that with respect to single variable it's actually major space है ना, वो हम एक्चुअली यूज कर रहे हैं. क्योंकि ये चीजें हम तभी कर सकते हैं जब आपके पास क्या होगा? मेजर स्पेस. आपको एक्चुअली इंटीग्रल से पहले आप लिख दीजिए, है ना, ये अपने ऊपर लिखना. इंटीग्रल से पहले लिख दीजिए आप सिंस दिस थिंग r1, then s1 lambda 1 is a major space, is a major space. So therefore we have this. Okay, अब आप देखिए लास्ट लाइन, आप देखिए chi ai of x, ये तो ऐसे रहेगा, बट व्हाट्स द इंटीग्रल ऑफ दिस? इट्स एक्चुअली द Lebesgue measure of ai bi, which is equal to bi minus ai. जैसे यहाँ पर आपने लिख दिया ना लिबेक मेजर ऑफ ए बी दैट्स इक्वल टू बी माइनस ए, so I can write this as summation I runs from 1 to k, then I can write bi minus ai first and chi aix, it increases to with respect to t, it's here b minus a times chi ax, okay, because the Lebesgue measure of AB is equal to B minus A. Now we vary X, and we know that this Rn, Sn, lambda n is a measure space, and X is a point of n tuple. Chi A, X, they are actually now step functions in the measure space. There are all step functions here. This sum, ये जो sum है ना phi k. This not now phi k, this may be psi k. Now if we denote this by psi k, so it's a sequence of step function such that psi k increases to this step function b minus a times chi ax. So if we define psi k, okay, define psi k of x is equal to summation I runs from 1 to k bi minus ai, then chi aix, okay, then this psi k is a sequence of step functions, in the measure space. किस measure space में है ये? X is in Rn, okay, in the measure space, this thing Rn, Sn, lambda n, such that it increases to psi k of x. It increases to psi k means this one. इसका लिमिट किसके बराबर हमने वहाँ देखा? It's equal to b minus a chi ax, which is again a step function. Which is a step function. ये भी step function है in the same measure space. वहाँ यहाँ पर लिखने की जरूरत नहीं है, तो लिमिट तो obviously इसी measure space में होगा जो आपने लिया है in the same measure space. Here it is Rn, okay, then Sn and lambda